the second 9 weeks ends up being more formulas rather than the proofs, which is sometimes better, sometimes worse, depends. Okay, a lot of vocabulary. Let's go through what all those mean. Okay, to get you into understanding why we would ever do this, okay, you live on a sphere, right? The Earth is a sphere. And if you look from a long distance, the outline of the sphere is basically just a flat circle. So it says this photograph was taken 216 miles above the Earth. From this altitude, it's easy to see the curvature of the horizon. Facts about circles can help us understand details about Earth. Okay, so things to recall. A circle is a set of all points in a plane, not in space. In plane. When we talked about it in space, that created a sphere. So points in space that are equidistant from a given point, and that's called the center of the circle. We had the symbol, a circle with a dot inside it, for the symbolism for a circle. Name it by its center point. So there's an interior and an exterior. I think that's where your notes start. Interior of a circle, interior just means inside. So interior is the set of all points inside the circle. Exterior is the set of all points outside the circle. The circle is actually the curved like pencil that you would draw with your compass. We will have a few constructions again, so we'll probably need those supplies now and then. All right, some terminology about segments and lines related to circles. Okay, a chord. It looks like it would be chord, but it's pronounced chord. A chord is a segment whose endpoints lie on a circle. So as you look at that picture, and some of you are drawing it, what segment has endpoints on the circle? What segment has endpoints right on the circle? AB. Okay. So a chord is segment AB. Have to use the correct symbol. If you put line, it's going to mean something different. So segment AB is a chord. A secant. A secant is a line. We have to use the line symbol with the arrows on it. Or remember how we could use just the script letter L to represent a line? A secant is a line that intersects a circle at 2 points. Now the secant in this picture is line L. If I put a name, let's say this is point E and this is point F, now I could use a different symbolism, line EF. Okay, so line EF or line L, depending upon which thing you're using to name it. That's a secant. Now a secant contains a chord. So if we look at this picture and emphasize just the segment from E to F, that is a secant. Segment EF is a chord. Line EF is a secant. So a chord is part of a secant. So when you're naming a chord, be sure you're naming a segment. When you're naming a secant, name the line. That's the difference between them. They both intersect or touch the circle at 2 points. And then we also have a tangent. A tangent is a line that intersects the circle at exactly 1 point. Now it does say it has to stay in the same plane as the circle. So in other words, this green line, the tangent line that they're showing, cannot be coming out from the board. That would not be considered tangent. It has to be flat in the same plane as the circle. Again, to name a tangent, you're naming a line. How would we name the green line that's up there? We use 2 points. There aren't 2 points on on the green line. So we would have to use the lowercase m. So we'd write out the word line, M. I know we kind of got lazy once we knew that the lowercase was a line, and we probably would just call it M. Can you use the line symbol? Not with what's there. If we put another point, like H, we could say it's line CH. Can't quite write that very good. CH. So you'll have to go with what's in the diagram, I guess, in order to name those different ways. The point of tangency is the point where the tangent line and the circle intersect. That in the diagram would be point C. Capital letter C to name a point. All right, we're going to look at another screen with those on it and see if you can name them correctly. Clarifying questions right now, though? Okay, let's try a set of examples. Okay, marker board. In that diagram, name the things that it's asking, use the correct symbols, and use what's available on the diagram to name it. Look at your notes to see what that definition was. Is it a segment? Is it a line? Is it a point? Didn't go over radius and diameter, but I think we previously talked about those. Segment what? Yeah, would be a diameter and maybe a chord also, which is. Now, pay attention to the correct symbols. Okay, on a chord, is a chord a line or a segment? Segment. Okay, so chords, I could have segment JM or segment KM. Was there another one? No, just those two. And remember, on segments or lines, you can reverse the letters and it's the same segment or line. You're just telling what the ends of it are. All right, a secant. A secant is a line. So your symbol is line. I have line JM. Was really the only line in the picture. So went through the circle twice. Tangent. How did you name that line that's on the outside? Can you call it H? No. Can you put the arrow symbol over it and call it H? No. You got to have 2 points if you're using the H. So the way to do that one was line M. Diameter, chord or let's see, segment or line is what I meant. Is a diameter a segment or a line? Segment. Okay. So segment KM is the one I found. Notice that KM was listed as a chord also. A diameter is a chord that goes through the center of the circle. So all diameters are chords, not all chords are diameters. So kind of the square rectangle idea, but related to these. And radii, which is plural for radius, segment LK or segment LJ or segment LM, those are all radii. Questions on those? Okay. Need to try one more diagram? Give me a thumbs up or down. Do you feel confident on being able to do that or not? Okay, so we'll go on then. Okay, back to your notes. We'll probably use the marker boards again, so just keep them on the top of your desk. It's fine. Okay, as far as terminology, we can have congruent circles. We've used the term congruent a lot. Congruent means things that are the same shape and size. Circles, they're always the same shape. So what makes circles the same size? What do you use when you draw a circle? Think about your compass. And what length do you set it at to draw the circle? You want the radius that you use? Okay, so to make two circles that are the same size, they need to have the same length of radius. So our definition, two circles are congruent circles if and only if they have congruent radii. So you can draw your diagrams you can put tick marks on there, you can write it out, but those two circles to be identical, congruent, their radius length has to be the same. Has to be the same in order to make them. And if the radius is the same, I would agree the diameter is the same length also. The definition mentions the radii because that's what you draw when you make a circle. Concentric circles. Concentric circles are in the same plane, so they're both flat on that same flat surface. They have the same center. So what's going to be different about them? The radius. Okay. You might have a radius of 3 for that one. You might have a radius of 4 for that one. So different size circles. A bullseye. Small circle, big circle, bigger. As long as they have the same center, they're concentric. I suppose you could have two concentric circles that are actually congruent. That would be two copies of the very same circle on top of one another. So not too interesting unless they have different size radius. All right, so concentric, same center but different radius. Then we go on to circles that are tangent. When we were describing tangent just a little bit ago, it was a line that was tangent to the circle. Now we're talking about two circles that are tangent. So in this context, tangent means touching at one point. So two circles that touch at one point would be tangent circles. Now there's two ways they could look. There are internally tangent circles. So these two circles, notice they don't have the same center, because if they did, like concentric, they would never touch. So the centers are at different points, but the blue one is pushed far enough to the side that it touches the red one at one point. Those two circles are tangent to each other. The second picture, the two circles are tangent. They touch at one point right there, but they're completely outside of one another. So they're referred to as externally tangent circles. So if you tie the term internal and external to the circles, that might help you remember which way they look. Tangent circles have to touch at one point. Internally tangent circles, one is inside the other. Externally tangent circles, the two circles are outside of each other, but they do touch at one point. Understand the difference between tangent circles and a tangent line? Tangent, we use that on other things. What else did we have that was tangent in geometry? You've heard tangent before? Okay, in relation to trig ratios. Trig ratios, is that what you were showing me, Molly? Okay, trig ratios with the opposite and the adjacent, yes, that was tangent. This is another time that we use the term tangent, but it has a totally different meaning. Okay, so here's tying back into the bell ringer. I want you to find the length of each radius, identify the point of tangency, write the equation of the tangent line. that goes through the point of tangency. We start in, find the radius for each one. That's the radius on each one. You can probably do some counting. If you needed to, you could use the distance formula, but I don't think that probably is necessary on my pictures. Then tell me where the two circles touch. What's the point of tangency? So if you can think back, the red line is the line that is tangent to both circles. Touches each circle just once. Think back to the bell ringer. What's the equation of that line? We're using up mostly on the point of tangency. What is this point where those two circles touch? Positive 2, negative 1. Okay, the first, our circle D had a radius of 3. If you can count vertically or horizontally, that would be the easy way. Going diagonal, I don't think you want to do that because that's not one space. That's like the square root of 2, square root of 2, so it'd be hard to do that. Radius of C was 1. A point of tangency was 2, negative 1. And did we get the line, the equation of the line? It's a horizontal one. So if you're thinking in these terms, x is supposed to be, the slope, it doesn't go up at all. Slope is 0. It crosses the y-axis at negative 1. We can leave out the 0x. So y equals negative 1 would be most likely the equation you were coming up with, the equation of the tangent line. Okay, I think we need to try a second one. This we didn't, I didn't have a second example. I was thinking I did. Okay, question on that equation of the line or any part there? Can you see that that line is tangent to both circles? It touches each circle just at that one point. All right, looking at some vocabulary, these two circles are tangent. Are they internally tangent circles or externally tangent circles? Externally tangent circles. Okay, the reason I did that is now we're going to focus on the line. Is the line an internal tangent or external tangent? Okay, so the next term, common tangent. What we're referring to is the line that is tangent to both circles. So this is what your first picture would look like. This one goes under common external tangents. So you have two circles. The two circles don't need to touch. They're not tangent that we're focusing on right now. We're going back to the lines being tangent. So this red line up at the top touches circle A at one point, touches circle B at one point. So that line is tangent to both circles. So it is a common tangent. Okay, same with line M, touches both circles. So how do I know it's a common external tangent, which will be different from the next screen that I'll show you? Okay, here's how you can tell whether it's a common external tangent. Consider the segment that joins center to center. A common external tangent line does not cross that segment from center to center. It does not cross it. Write some notes about that. A common external tangent line does not cross the segment connecting the centers of the circle. The common external tangent line does not cross the segment from center to center of the circles. It's tangent to both, and it stays like on the outside. It does not cross from center to center. Now if you compare that to my next picture, you'll see a difference. So the next picture is a common internal tangent line. If you would connect center to center here, notice that the line crosses it. That will be a common internal tangent. The common internal tangent touches each circle, but it goes kind of between them. Crosses the segment from center to center. So there's some confusing terminology here, and what you need to look at as you're trying to unwind it in your head, are we talking about the lines being tangent or the circles being tangent? And then is it internal or external? Is it like inside or between? Or is it outside of? To help you out. So let's draw some pictures on the board while you're trying to finish up some notes there. Okay, 2 circles, or maybe you could draw. Why don't you draw, grab your marker board. I'm going to ask you to draw me something. Okay, I want 2 externally tangent circles. 2 externally tangent circles. When I asked you to do that, did I mention anything about a line? No, so I don't need to see a line. I need 2 circles. They have to be tangent, so they have to touch, and they have to be external of each other. Show me what you drew. Let's see. Right, don't erase it. Okay. So you got the snowman idea. So now I want you to see, can you draw any lines on that picture that are tangent to both circles? Or could you draw a line that's tangent to both circles? There might be more than one. Line that's tangent to both circles. That's an idea? Ones I'm seeing, and mine's maybe turned differently than yours, but some are giving me the line like here. Okay, didn't get a tangent. bit more. Okay, now before I go on, is this line a common internal or external tangent line? External tangent line, because it does not cross center to center. And then some of you had the other ones drawn on this side. So that's another common external tangent line. Then I also saw, I have too many different colors here, the line that went through right here. Did everybody think through that one? That's tangent to both circles. Is it a common internal or external tangent line? Internal, because it does cross the segment from center to center. So the green one was a common internal tangent line, the blue were common external tangent lines. The circles were externally tangent. Okay, erase that one. Draw me two concentric circles. Without erasing it, concentric circles. Okay. Tangent lines. You draw a line tangent to both concentric circles. Okay, can't do it. You can make it a tangent to one. If it's tangent to the little circle, what is it for the big circle? Draw it in there and take a look at it. I don't know if it'd be a diameter. It kind of depends how. It wouldn't be if they're concentric. Draw a tangent to your little circle. So what is that for the big circle then? Secant. Okay, what else could I do with that? Probably nothing. Okay, draw me two internally tangent circles. Internally tangent. Okay. Now try tangent lines. Lines tangent to both. Did you get more than one? Two circles are not internal. One beside the other. Seeing the same thing. Is anyone coming up with the second one? I'm seeing this circle and then a smaller circle and you're giving me a line like here. So that's the only one that you came up with? Okay, that's true. Is that a common internal tangent or external tangent line? External, because if you connected center to center, that segment, your line isn't crossing it. So that's a common external tangent line. All right, getting the vocabulary figured out? All right, let's try an experiment using your iPad. You can either use that geometry pad or GeoGebra. Hopefully this can be done in either one of them. We haven't used them for a while. Got two things that I want you to try, so I'll give you a few minutes to see if you can create one or both of them. So get into that program, whichever one, the app or the program that you're using. I need you to draw a circle and a tangent line. You might look through the choices and see, like in GeoGebra, is there a choice of tangent line? I think there is. I have to remember what something like that. Oh, it's pretty creepy. To draw a circle, I think you probably touch where you want the center to be, and then touch like where you want the radius to end. You got a circle in a tangent? Okay, then read my next direction. The tangent, you might have to touch on the circle where you want the tangent to be. You probably can't just eyeball it. Is there a choice of tangent? How many are in GeoGebra? Okay, I think it's maybe going to work better in GeoGebra. Does it look like in the geometry pad, you can't choose tangent unless you have the purchase one? So switch to GeoGebra if you went into geometry pad. Circle. Maybe just, yeah, that first one, just touch where the center. Radius, tell it the length, give it a number for the radius length. So there's a small circle. Now like, there's a place you can choose tangent. Select the point or line within the circle. Circle. Are we getting tangents? Okay, once you got a tangent, it says form the segment. So go to just the segment tool. Segment and touch the center and that point of tangency. So what did you really just draw? The radius. Okay, now find where you can measure an angle. And it goes clockwise, or actually it goes counterclockwise. So if you don't get the angle to show up where you thought, try it again. Remember the middle letter. You might have to have a point out on that line, possibly. You might have to put another point out on that tangent. Now that I'm thinking about how you measure it. It's weird outside. You try putting a point on this tangent, like under A. You can do a point on. Now trying to measure the angle. You've got 3 points now. You have to go to the vertex. The vertex has to be the middle one. Remember how you name our angles? Go A, B, C. Are we getting that angle measured? The point of tangency has to be the middle one. Okay, what angle are you finding? Okay, for those of you that are having trouble getting it set up, here's what it should look like. It should have a circle, and there's a point on here where there's a tangent line, then you're connecting those two and measuring this angle. You should find that that angle is 90 degrees. We'll have a theorem that tells us, we have a theorem that would tell us a tangent and a radius are perpendicular at the point of tangents. Raise your hand if you got that to work on GeoGebra. It wasn't exact? Yeah, I guess, I'm wondering. Okay, so what part do I need to clear up?
Well, just not, there's not like a tangent line option.
I think there is. Are you on GeoGebra? GeoGebra? Okay, yeah, there was a tangent line option. And I think you had to touch a point on the circle and then the center or the actual circle maybe. Zach and I were messing with it to try and get it to work right. So there should have been a choice where you can do an exact tangent. Find it now? Okay, so quite a few got that to work, not everybody. Let's try a second one. In a second one, draw a circle and two tangent lines. A circle and two tangent lines. And then follow the rest of the directions up there. Select the center point. Let's try a tangent. I did this last time. I did one tangent. And we need another point on there. Okay, are you getting two tangents on the same line? Or a same circle, I mean? I think you have to put a second point on the circle so that you can make the second tangent. Under the pointer A part. Okay, so how do you do that one? Okay, I think you first make your circle. At least looking at what Paige and I were doing. Make a circle, you've got a point. We used the first option, I think it was, where you're making a circle with a point on it. Okay, so like this is A, this is B. Then tangent, touch point V and touch the circle, and it will make a tangent through point V. That's just like what you did on the first one. Now to get the second one, I think you have to make another point. So go to the, I think it was the A at the top. Use the point on object. Point on object. And when you touch it, don't go completely over here, but I'm going to go about a quarter of the way from point B. Can you get another point on your circle? Then have it do a tangent through point C and the circle. I should draw you a tangent going this way. Okay, and I could create a segment from the point of tangency to the can you just tell it to make a point where the two tangents intersect? I think that's still under this A option. Can you tell it just to put a point at that intersection? My second step there, I need to kind of change. I don't need that one. Okay, what I want you to measure then, measure the distance from C to D, and measure the distance from B to D. I'm just kind of putting beside it so that you know those are the ones to measure. You could do distance between 2 points. Are you able to do it that way, or do we have to create a second? You can do it that way, distance between 2 points. What should happen? Okay, what should happen? Okay. Those that are getting it done correctly, those two lengths are the same. Those are called tangent segments. They go, I guess my explanations up there is right, but from the point of tangency to the intersection point, that segment is a segment on the tangent. Those two segments are congruent. Some of you like investigating, some of you don't. Yours were not the same? I'd have to kind of go through. Did you make the tangents or did Deb make the tangents? That's weird. Okay, let's go ahead and take a look at the theorems. So I think there's 3 total theorems if you go back to your notes. The first 2 sound like converses of each other. It's whether you know it's a tangent or perpendicular to begin with. Okay, the 1111, if a line is tangent to a circle, so the hypothesis here is you know the line is tangent to the circle. It says, then it is perpendicular to the radius drawn to the point of tangency. And then they just abbreviated it. So this first one starts with the line being tangent, and the conclusion is that the line is perpendicular to the radius. So radius and a tangent make a 90-degree angle. So the second one, we start with the perpendicular. Just some random line is perpendicular to a radius at a certain point. Thank you. On the circle. So the perpendicular is what you're given, and what you can conclude is then M evidently has to be a tangent line. So you'll use the second theorem here if you were trying to conclude whether it's tangent. First one, you have to know it's tangent, and you come up with the 90-degree angle. Got your drawings and information on those? No? Okay, first one, you have to have a tangent. Second one, you have to have a perpendicular to begin with. There is a construction on this page. I don't know that we'll do it today. I think we'll kind of do all our constructions together. But we can construct a tangent to the circle by constructing a perpendicular. It's been a while since we did that, but we did construct perpendiculars previously. I got what you mean? Okay, let's see how we would use these in some samples. Okay, Okay, this is probably one you want to draw on your examples, maybe the backside of the first page or something like that. Okay, my directions say that line BH is tangent to circle C. Now the theorems that you just wrote down, if we have a tangent to a circle, so line EH is tangent, and the radius CH comes to the point of tangency, what did you just discover and write down about a tangent line and a radius that meet? They're perpendicular. So that would mean that angle's a 90-degree angle. So in my diagram, do you see a right triangle? We're going to use the right triangle as we solve this. So we have the line and the radius. We're supposed to find the length of EH. So how long is this segment? Well, it's a leg of the right triangle. What can we do to solve right triangles? Pythagorean theorem, trig ratios, 30, 60, 90s, 45, 45, 90s. What do we have that we can use here? This length is 4,000. That's what it's trying to show you there. So this side is 4,000. CE. How far is it from C to D? That's a radius of the circle. Notice CD would be 4,000. And then DE is 1,000 more. So what's the whole length of EC? 5,000. Total. That's the hypotenuse of the right triangle. So how can we find EH? We can do Pythagorean theorem. We've got some big numbers to work with, but I'm going to put an X. Okay, so X squared plus 4,000 squared equals 5,000 squared. Anyone notice a multiple of 3, 4, 5? So I know it's going to be 3,000. But plug through the actual numbers. 3,000 is EH, and it was miles. I just took a shortcut on the Pythagorean theorem. Lots of zeros. Now think how that picture is. We had the radius and then we went above it. The next one is going to be just a story problem. They like to do some story problems related to this. Like the circle would be the earth, and then something's above the earth, maybe flying, or I think they do one where it's the top of the mountain. That extends the hypotenuse to make it a little bit longer. So a type of story problem would be this type. Let's try and make the circle picture. Early in its flight, the Apollo 11 spacecraft orbited the Earth at an altitude of 120 miles. That's how far above the circle. That's the extra part to add on to the hypotenuse. What was the distance from the spacecraft to the Earth's horizon rounded to the nearest mile? That's like what we were trying to find in that last picture. So here's a cross-section of the Earth. The thing is orbiting above the Earth. We're going to form that same right triangle with the tangent and the radius. They're asking you to find this distance from the thing, from the Apollo 11 to the horizon. That's the point of tangency. This is what they're having you try and find. 4,000 was the radius of the Earth. 4,000 and how much above the Earth? 120. So your hypotenuse is going to be 4,120. Think through how the story is worded. You understand where their information's coming from and where it goes on the picture? So then you're simply doing like we did on the last one, Pythagorean theorem to solve it. I think probably more than the Pythagorean theorem. Do you understand how to set it up? The amount above the Earth is what you're adding onto the hypotenuse. Does it 900 and something. Let's see. My solution shows 987 miles. Looks like I put the step by step here. Okay. All right. That last theorem, now let's see. Okay. Kilimanjaro, this was the one. They're talking about a mountain being here. Now this one we won't have time to do, but I put in feet and miles so that you had to do some converting. So although it tells you how tall Kilimanjaro mountain is, you need to convert it into miles in order to add it on. All right, the last theorem is a simple one, and that was the second investigation you did. If you have two tangents, these two segments, those tangent segments will always be congruent. So your hypothesis picture, got a circle with two tangents, and the two tangents meet at a point outside the circle. So the segment from A to B and from A to C will be the same, as long as those are actually tangents. So Megan, I'm not sure what your diagram was doing different, but something wasn't set up right. So they will simply, I'll show you a couple examples before I list your assignment, I guess. Got what you need from the pictures? Okay, an example would look like this, for instance. You got two tangents. You're just going to set those two equal and solve. That one's not too difficult solving. I think they throw a fraction into one. It does say find HG, so don't stop with 12. Put the 12 in and calculate what it was. You might look at the solving on this one because you'll probably need a reminder. I'll let that up there for just a little bit. So you can look through how did they solve? What did they do from this step to this one? How'd they get rid of the fraction? Multiply each side by the denominator. Get rid of the fraction. So those theorems are not hard to work with. Get familiar with what they look like. This is on that e-backpack list, but today, page 751. And remember I gave you the cumulative test. What did you decide? You have to do about 10 a day to get you there. So try and do the first 10. There are things at the end of that cumulative test that are chapter 11. We will have covered it by next Thursday, but realize if you get real far ahead, you'll probably run into a few things that we haven't covered yet. So, hope that matches up what we have on the backpack. If you have some supplies, a compass and straight edge in your locker, please bring those back. We'll need them for this chapter.